Shekhar from IIT Kharagpur. Professor Shekhar is the Vice Chancellor of Andhra University and a distinguished mathematician with a PhD in mechanics from the University of Hyderabad. With over 27 years of teaching and research experience, he has published more than 110 papers in international journals and supervised many PhD scholars. He has received numerous honors, including the National Mathematician of the Year 2023 with the JPS Gold Medal 2018, Fellow of the National Academy of Sciences India and the Alexander von Humboldt Fellowship. He is a member of professional bodies such as the Indian Mathematical Society, the Indian Society of Theoretical Applied Mechanics, and Andhra Pradesh. Yes, sir. Yes, sir.
Please go ahead.
Okay. The Andhra Pradesh Academy of Sciences and editorial boards of leading journals. We are delighted to have you, sir. You can continue with your talk. Thank you.
So, good morning, everyone. So, can I proceed? Is the screen visible?
Yes, sir. It's completely visible.
Okay, so how much time I should take?
For 30 to 40 minutes.
Yeah, okay. So, good morning, everyone. First of all, thanks to the organizers, Dr. Deswal and the colleagues who have invited me, and my apologies that I could not be available physical mode due to various constraints. So, today's talk is on modeling of multifacial models for enhanced oil recovery. So this is a joint work with my past PhD student who is now a postdoc at University of Stuttgart, Germany. So those who are not aware of oil reservoirs, so they might be under the impression that it's also like a water well where you dug up a well and then you have a oil well and then you put pump and suck it. So unfortunately, that's not the case. So typical oil reservoirs, oil is trapped in a rock, which is micropores. So there will be an injection well or number of injection wells. And since oil is immiscible with water, with high pressure water, it is called water flooding. So water is pumped so that water displaces oil, and then there is a collection well from where this production well oil is collected. So now in this case, the entire reservoir is in horizontal mode, okay, in this mode. So in this picture, you are seeing this is the displacement happening because of the immiscibility. And if you see this displacement, this is inside the rock, micropores. This displacement is not very uniform. It depends on various factors. There are a lot of instabilities. So sometimes the spatial instabilities, sometimes the direction instabilities take place. So the challenges here is how to extract more oil. That's the idea. And understand the instabilities. So that's, and typically reservoirs cannot be gone and then go for experiment there and then say that, okay, after experimentation, this reservoir is not good, let us come back. So it won't work that way. So what is the challenge here? You do all the experimentation, data collection from the reservoir, do the experimentation in the laboratory, in simulations. Then after getting a good picture, then go to the reservoir and then perform the actual extraction. So there are a lot of limitations. Earlier, thermal techniques used to be there because if you heat, the viscosity changes, surface tension changes, and then due to the temperature gradient, oil is displaced and it is collected, but this is not environmentally and financially not viable. So what is a key technique is water flooding technique. This is established technique. And key factors, as I mentioned, heterogeneity means spatially varying, anisotrope means directional dependency. So 2 phases, oil in water, and typical laboratory experiments and numerical simulations are popular, offshore experiments. So those who are new, so if you take a particular volume and put some solid particles, the empty space is called the porosity. So that means the volume fraction of the empty space is called porosity. Permeability is the ease with which fluid can penetrate. So for example, it is permeable this way, but impermeable here because there is a block, right? So whatever fluid coming here, it can come here, but it cannot come here. So impermeable. So that is the ease of penetration. But if you have more than one phase, then each phase is denoted by alpha. So here water and oil. So alpha W, alpha oil. So then total saturation is equals to 1. That means in a particular volume, water phase, oil phase is normalized to 1. And this is the relative phase saturation. Okay. Then another important thing is called wettability. Since the oil is sitting on the rocks, so if there is water and if the contact angle is less than 90, then it is called water wet. How the contact angle is happening? It is due to the balance of cohesive and adhesive forces on the rock surface. If the contact angle is larger than 90, then it is called oil wet, and this is intermediate wet. So this contact angle is also important for oil recovery models. Then since the oil is trapped in micropores, therefore for these micropores there is a pressure competition between wetting phase to non-wetting phase. So that's called the capillary pressure. And this capillary pressure depends on various factors like surface tension, contact angle, porosity, permeability, and a saturation function, which is called a flux function. This is several correlations are there, so people have to experiment various such saturation functions. Then within a porous rock structure, oil may penetrate in some fashion, water may penetrate in some fashion, hence the relative permeability also matters. Alpha is phase permeability, this is a absolute permeability, and this is a relative permeability of each phase. So now let us understand about the heterogeneity. So each block is homogeneous with the permeability 200 millirc. So 3 blocks are kept aside with a different varying permeability. The entire block is now heterogeneous because the permeability is varying with space. Okay. So these colleagues have done some experiments using foam injection and gel injection. So since it's a small scale experiment, water injection won't give enough pressure to displace. So at laboratory scale, foam injection and gel injection tests are performed in this 3 block structure. You can see a lot of oil gets trapped. You see the block 1, block 2, block 3. So oil is here, but even after displacement, there is a lot of oil left. So the heterogeneities are causing this some instabilities. So still there is an unswept area and high permeable or medium permeable and low permeable. So it's not that if it is high permeable, then flooding will push. That's not happening. Low permeable also not happening. So the spatial differences are creating some challenges. Then how much recovery of the oil in the foam case and gel injection case, the oil recovery after first injection is done with the foam and gel, then water flooding also is given. So the total recovery in case of foam 60% and in case of gel close to 50%. But in real scenario, you won't see this. So large scale simulations, you will see a little later. So the direction, the spatial dependency, which is the heterogeneity, is a challenge. So how do you model it? So those who are not familiar, typical flux balance model. So what is that? So those who have studied physics, electricity, magnetism, you might have heard of Kirchhoff's law, or in chemical balance, something called Fick's law of diffusion. So that means the total flux is proportional to the gradient. Let it be Fourier law, for example. That means the flux is proportional to gradient of temperature. Similar fashion, the Darcy's equation is flux of each phase is proportional to the corresponding pressure gradient. This is the gravity forces. Then, how do you determine the proportionality constant? Suppose you have oil and water. If you keep the remaining things constant, if you keep the pressure constant, water will give more flux, oil will give less flux because of the viscosity. Therefore, viscosity is in the denominator. Whereas, if it is more permeable, more flux. Therefore, permeability is in the numerator. So this is a typical Darcy's equation. Okay. So this is a Darcy velocity, pressure of the fluid phase or pressure of the water phase, density, then viscosity, relative permeability, absolute permeability, and gravitation. So this is a typical Darcy's equation, which is equivalent to Fick's law of diffusion or Fourier's. So then you need a typical mass balance. So that is called equation of continuity. So this is right hand side is if you have some sources or sink, and this is a local rate of change, and this is a total mass flux. So these two equations are the typical governing equations, which will be written for each of the phases. For oil phase with the alpha W, water phase with alpha W, oil phase with alpha O. And this is the total saturation constraint, and this is the capillary function. Now, there are two types. This is called co-current, but which means injection well is here and production well is here. Water is pushing oil and both are collected. Counter current is you keep a block, push oil through water, then oil through backflow, it is coming here. So this is called counter current. So for to start with the homogeneous case, just for our understanding, this equation is substituted. This equation is substituted here. Okay. So then you will get equation for saturation and in terms of capillary pressure. That's what you are getting. So capillary pressure has some model which I have discussed using Leverett flux function. So it's a highly nonlinear because the capillary pressure is a function of saturation and hence it's nonlinear. So this equation for homogeneous 1D case, this is equivalent integral formulation, and then we use something called channelized separation of variable, and then we get the solution. Early time solution, long time solution, and a hybrid solution using a Heaviside function. Okay. So this we compare, and then it natural that homogeneous case is agreeing with existing studies, etc. But the story is not that. The question is it stable? Whether this water flooding will uniformly displace or somewhere more, somewhere less, and water is going faster. So that's the question. So that can be visualized as follows. This is at the beginning of water flooding. Then you can see after some time, then this is called a breakthrough. What do you mean by breakthrough? You can see some white patches. That means oil is trapped. oil is trapped. After some time, these fingers got merged. These are called fingers. They got merged. That is called breakthrough. After breakthrough, whatever oil is trapped here, you cannot recover. You will not be able to recover. So, these viscous fingers could be due to direction dependency. So, hence, we have to understand about these viscous fingering. You see, these instabilities are giving us this viscous fingering model. So, if this finger and this finger merges, then there will be a lot of oil trapped that you won't be able to extract. So, these are the finger structure, but as a mathematician, it's very hard to trace the locus of these fingers and then incorporate in our model. So, we approximate with something called an effective finger. That means all these fingers are equivalent to one single effective finger with the mean radius, this, all the, and then this effective finger is given into the model, okay, into the Darcy equation for each phase, where the fractional finger cross section is a function of all the parameters, and permeability, porosity, contact angle, viscosity, saturation, all that. So this model is incorporated, and we use a implicit pressure, explicit saturation scheme using finite difference method. Then we want to test with some models of permeability and porosity. So in the first case, porosity is exponentially decaying, permeability is just a constant multiple of porosity. Model 2, porosity constant, permeability is exponentially periodic. Model 3, porosity is random, permeability is a constant multiple of exponent of porosity with a positive exponent. Okay. Then the fourth one is a porosity is random, but the permeability blockwise changing. So for one block, first model, second block, second model, third block, third model, and the last block, something called Karman-Kozeny correlation, where it depends on mean particle diameter of the particle packing in porous medium. It is something like if you put rice in a small container, the packing is different. If you put, say, mustard, the packing is different. If you mix rice and mustard, the packing is different. So the mean particle diameter and the porosity, this is the permeability is varying like this. So this block structure, then we want to study the solution. So the normalized water saturation indicates how much oil gets extracted. So in model 2, which is the exponential periodic, you have a large delay. This is from the distance of the inlet 1D, and this is the production well. So you have, for example, model 3, rapid, very rapid saturation. That means water, normalized water saturation is 1, and then it is dropping. That means oil is enhanced, right? So, but this is not realistic. Then if you have a block, this is the variation is, so this model. Region 1, region 2, there is a discontinuity accordingly. So this gives an idea how your saturation is drastically varying from model to model. So therefore, without proper analysis estimate, if you go to the oil reservoir with this, then you will get a shocking results. So hence, one has to be very careful. But we have implemented our effective finger model, as you can see. This is effective finger model. So we have solved that. Then this is a classical model. Then this is the effective finger model. So as you can see, effective finger model is delaying, slow. So that means this could be a real scenario. Okay. So that's the idea here. So we have understood heterogeneity in a piecemeal manner, not in concrete manner. So we want to understand the heterogeneities in a very more concrete manner. So for example, you see here with the time, each model how much recovery. So third model, the block model, low recovery. Okay. So fourth model, the block model is very low jump. Whereas the third model, the saturation is very low. And then first and second, they are competing. Okay. So there is a drastic variation with a heterogeneity. So that's a summary. But that is not enough. The effective finger model may not capture the real scenario. So it is like this. Suppose those who are online, when I'm taking this lecture, some of you might be watching a movie, some of you might be watching, chatting with WhatsApp to some people. So those who are sitting in the class, they might be doing notes on some other topic, or they are chatting with friends. These are local oscillations. But if somebody is watching as an observer from outside, they will think the class is happening pretty nicely. That is the macro. But if somebody closely observing inside the class at every individual micro scale, then you will know whether that person is paying attention or the person is doing something else. So these micro scale oscillations should be reflected in the overall solution. That means somebody should be able to observe, yeah, there are disturbances, I can see somebody is chatting, somebody is writing some other notes, but overall this class, coefficient of this class is this much. Okay, so that's called the upscaling. That means the oscillations are there, but including oscillations, this is the coefficient of the class. Then the coefficient is good or bad. So in a class, if 50 class, 40 people are doing this business, then if that is reflected in the solution, then you get a very poor coefficient. Okay. So how do we do that? That's called upscaling. How do you capture local oscillations and upscale? So we want to create local oscillations, block after block. That means this individual is attending class seriously. This individual is doing some disco drama, that is YouTube or something. So now you put periodic, repeat, and then try to analyze. Okay. So there are discontinuities. So now, since it is a heterogeneous, we repeat large number of blocks, types. Somebody is studying, somebody is watching YouTube, somebody is chatting with WhatsApp, somebody is writing some other notes. So variety of oscillations are there. We want to understand these local scale, upscale to large macro scale and see the variation. So these are 1D equations again. Then you introduce the scaling that I mentioned. Then you try to get the upscaled equations. This is called asymptotic way of homogenization. So at each block, there is dynamics happening. At each block, flux is continuous, but the pressure, there is a jump. So with that, we introduce this two-scale model. That is, X is macro scale or slow variable, Y is micro scale, fast variable. What do you mean? On distance, if you are seeing the class, it's a macro scale, so you will not see the disturbances. You will only see that somebody is moving the hand, somebody is moving the head and talking to the next door neighbor. Just overall, you will see something happening, kuch ho raha. But on micro scale only, you will know kya ho raha, what that person is doing. So these two scales are relatively competing with this parameter epsilon. And this is the cell and there is a discontinuity in a cell. So multiple discontinuities we have created. So in I-1 block, 2 sub-blocks are there with the porosity 1, porosity 2, permeability 1, permeability 2. Then in I block, same porosity, same porosity, same permeability, same permeability. So 2 blocks together you repeat. Okay, so this is a periodic structure. With this, you go for asymptotic expansion in terms of these cell variable and capture the upscaling technique effective equations. So finally, this is called the effective equation with the 2 cells, where this flux function has the information of these upscaling. So this mathematical technique of homogenization is used, where phi and k are now at each scale they are varying, so the micro scale. Then let U epsilon be solution satisfying the matching conditions from one cell to another. Then 2 scale asymptotic expansion of the variable at the cell level. Then Uj are periodic in this fast scale. Then asymptotic expansion of the pressure is also done. Then the flux function is also done. This is expansion of the flux function. Then collect the coefficient at each epsilon order. Then you get to the block structures, how the flux jumps from block to block. Then you get the effective equation. So, end of this homogenization process, you are capturing the local oscillations into this solution, which is called upscaling. So, the upscaled fluxes are, it's a little complicated, but no problem. Then we want to do this with multiple cells, discontinuities. So, instead of 2, 4 we have created. 5, 1, 5, 2, 5, 3, 5, 4, 5, 1, 5, 2, 5, 3, 5, 4, repeated. K1, K2, K3, K4, repeated. But from block to block, there is a discontinuity, see 5, 4, 5, 1. So this is we call original approach. For computation purpose, we shifted it. You see, block is now shifted. What is the advantage? Computational block, half of it has 5, 1, other half has 5, 1. So there is no discontinuity. So computationally, this saves so much. So 2 approaches we have. And what is the structure of the porosity permeability? One is staircase upwards. That means increasing porosity permeability. And the other one is the staircase downwards. And this is random. So 3 cases we have implemented. Then the equations, effective equations are discretized on a staggered grid. And you compute the solution. So here, average constant porosity, upscaled constant porosity are mapped side by side. You can see from the inlet to almost close to the middle, upscaled is slightly overperforming, but later on it is underperforming until saturation is occurred, and towards the end there is a small crossover. But if you see micro scale solution, there is a lot of oscillations. Just if you plot each cell you compute, then the discontinuity solutions are there. But in upscaled, those discontinuities are hidden, they are incorporated, and you get an effective solution. So this gives how the solution contains these variations, local oscillations. Then this also, you can see upscaled Karman-Kozeny is overperforming, upscaled large permeability is underperforming. Okay, so you have to see the soil structure, analyze, identify which range the porosity permeability is fitting. Accordingly, you will get the idea. So here staircase upwards, first model. Then this is a staircase downwards. Okay, staircase upwards. you can see upscaled original approach, and this is upscaled shifted approach. So shifted approach is underperforming until close to the middle of the length of the reservoir. Then later on, it is slowly, sharply going. Whereas the upscaled original approach, even though it is outperforming, but the saturation is getting little longer distance from the inlet. So typically, what is happening in the middle, we are not so much interested. What is happening towards the outlet, we are more interested. So that's that gives an idea of depending on the structure, and this is a micro scale oscillations are there. Okay, so this gives an idea. So then you have to understand what is the soil structure, and accordingly which solution has to be understood, and then do more test cases. Then with the current efficient data-driven techniques, you can maybe derive a quantum system. Then I'll summarize direction dependency now. So far we discussed spatial dependency. Now the permeability could be a tensor. It will change in each direction. So instead of taking full 2 by 2 matrix, we have taken only diagonal matrix kxx, kyy. There is no kyx and kxy. They are zeros. So your permeability matrix, which is a tensor, contains only 2 entries kxx, kyy. That is like it is variation along only principal directions. Okay. So now the competition parameter plays a role. The ratio of kxx to kyy play a role. Two models we consider. One is a narrow channel model. Another is a quarter 5 spot. So quarter 5 spot, inlet is here and outlet is exactly at the diagonally opposite. And a narrow channel, inlet is here and outlet is here. Okay. So typical reservoirs, quarter 5 spot models are used. So in the narrow channel model, this is a competition parameter kxx to kyy. If it is low, which means the permeability along the vertical direction is dominating. So once you are pushing water, it is going towards the vertical direction and taking the support of the wall. Whatever pressure you apply, it is going only along the wall with the support of the wall. So the oil in the middle is getting trapped. This is called oil bulb. If such bulbs are many, we will not be able to recover that oil. Yeah. So wall effect. This is a wall effect. Okay. So this is how oil bulb is getting formed. Okay. So these are the things what I'm. Okay. So the oil bulb formation is seen here. Okay. So this gives for each of the anisotropy ratio, what is the oil saturation, okay, across reservoir length. Then recovery percentage, as you can see, if the anisotropy ratio is low, the recovery percentage is less. If the anisotropy ratio is high, it's almost permeable. So everything is, that means there is no rock. So naturally, whatever oil is there, it is getting pushed. Okay. So this is not the real scenario. The scenario could be somewhere intermediate in these two range. The best of the best could be this. So even that, you are getting less than 50%. That is the precise reason that your reservoirs, a company takes a reservoir, keeps it for ages, 25 years, then only it will abandon the reservoir. The second one is quarter 5 spot. You are pushing water and oil is getting pushed and extracted from exactly diagonally opposite. But in this process, you can see a lot of oil is trapped. Okay. So here also the wall effect is there, but since the area is more, the spatial area, so it will certainly take the support of the wall. So now you will see the oil bulb form. Okay, so that's what you have seen. So the oil bulb is also, see the gap here, that is the presence of the oil bulb. So if the anisotropic ratio is 100, then you are getting full extraction, which is not the real scenario. If this is anisotropic ratio, this much there is an oil bulb, that means there is it will give the flux how much oil is trapped. So here, for this realistic scenario, see, only this much percentage of recovery you are getting. So even if you wait for long days, the recovery is very slow. So the companies go for primary recovery, secondary recovery, and something called tertiary recovery with the various other techniques. Then by the time the company abandons one particular reservoir, it will be something like 40% of oil is still left in that reservoir. So we are interested in estimating breakthrough time at the when you take both. We are interested in recovery percentage at breakthrough time. Okay, so that is understood. For narrow channel, recovery percentage is high, but for the with anisotropy ratio for quarter 5 spot, it is very low. But we are interested in classifying the reservoirs with some correlations. That's what we have done. Based on these correlations, we have estimated quality of a reservoir, and you take the characters of the reservoir data, check where it fits, then it will give, if the quality is here, how much recovery. If the quality is here, how much recovery. So that estimate we have shown it. So in summary, upscale model is giving information on spatial dependency of the solution, whereas anisotropy is giving variations in the direction dependency of the solution, and correspondingly the recovery percentage control mechanism. So this is my student, and we have published some, and this is my colleague from mining engineering. So this is the work, and these are some porous media basic books and oil recovery. For example, viscous fingering, there is a literature is available. Thank you very much for this opportunity. Any questions, I'll be happy to answer.
Any questions from the participants?
Thank you, Professor Shekhar, for giving a wonderful lecture and explaining with examples of the concepts of micro oscillations, macro oscillations, and upscaling, and how to form the blocks and various models that you have explained here. And we are thankful to you. I hope our participants will be enriched by the understanding, and they will have the understanding of the theme, and it would help them to do their future. Thanks a lot once again.
Thank you, sir. Thank you. Namaste, everyone. Thank you very much.
Thank you so much.
Thank you.
Now it is over, or we have some other speaker also?
Sir, it's over. So the others would not be able to join us.
Okay, I'm thankful to all the participants here.
Sir,
Yes,
sir, I want to present my presentation.
so you can ask the organizers.
Golden,
Yes, sir. Yes,
you
sir.
would be able to आप स्टूडेंट है या फिर आप फैकल्टी हो?
A student.
ओके, सो आप ना क्वेरी ग्रुप पे डाल दीजिए, आपका दूसरे सेशन में प्रेजेंटेशन होगी.
Okay.
थैंक यू सो मच.
So,
Thank you.
okay, thanks a lot for this wonderful session.
थैंक यू सो मच सर.